All right, from this video, let me proceed with the new lecture slides I posted in the Coursera site. All right, and in this video, the topic is the chainer. That is a very important technique of differentiation. So the basic idea of the chainer is, in the previous video, we studied how to compute the derivative of sum of two functions or difference between two functions and or the product of two functions or division between two. So now the last thing is, in this video, we are going to study how to take the derivative of composition. So I guess you guys have studied this composition, a way to compose two functions. And composite function is composed of one outer function and one inner function. So outer function f has the input as another function. So the outer function has a another function g as the input. Okay? So f of g of x, or it is often denoted by this empty circle or open circle. So you should distinguish from product. We if we so if we write the product, we use a closed circle like a dot. That means the product of these two functions, but the open circle, we represent the composition or composite function of two functions, f and g. So to remind you of this composition, let me show you a couple of examples. So in the first example, we have a function f of x given by 2x plus 5, and g of x is given by another function of x, 3x squared. So f of g of x, so originally f of x is 2x plus 5. Now this is going to be the outer function of this composition, right? So now the input is going to be g of x. So instead of x, we substitute 3x squared. So f of g of x is a 2, 3x squared plus 5. So that is a first composition of this between these two functions. So 6x squared is 5. Okay? Now we change the order, so g function becomes the outer function of this composition. Okay? And originally g is 3x squared. G of x is a 3x squared. Now we compute the composition of g of f of x. So instead of x, so we replace this x with f of x. So 3 times, instead of x, we plug in 2x plus y squared. So this is going to be 3, 2x plus 5 squared. So whenever we compute the composition composite function, we should be careful about which one is the outer function and which one is the inner function. So depending on the order, we have a different. And just let me show you one more example. Now we have here two functions of y. So p of y is given by y minus 3. Q is given by iq. And p of q of y. So p of y was a y minus 3. So now in place of y, we substitute y cubed. So y cubed minus 3 becomes the first composition. And the second composite function is now q of p of y. So the outer function is y cubed. So q of y is given by y cubed. Now instead of y, we plug in p of y. Yeah? So this is going to be p of y cubed. So y minus 3 cubed. All right, and the chain rule tells us how to take the derivative of a composite function. So if we have function f as the outer function and the function g as the inner function, so the way to find the derivative of f of g of x, okay, is we first take the derivative of the outer function, okay, so f prime, and we leave the inside function g of x alone, and then multiply by derivative of g of x, the derivative of the inner function. Okay? So that is the first expression of the chain rule. There is another equivalent expression. So now we have two functions. Function y is given by a function of y, and so the input is denoted by y, and its output is denoted by z. Okay? And there is another function g has the input x and output y. Okay, now you can see the composite function, outer function becomes f, because now f's input is y. That is a function of g of x. Right? So now the way to find the derivative of z, so the final output with respect to the first input x, so dz over dx, derivative of z with respect to x. Now we first take the derivative of z with respect to y. That is the derivative of f. Okay? So that corresponds to this part in the first expression, f prime. Okay? And then we multiply by dy over dx. So g prime. Okay? So now you can see the infinitesimal change in variable y will be cancelled. So we obtain dz over dx. Okay? So that is one way to prove the chain rule. Dz over dx, the final input, infinitesimal change in final input over infinitesimal change in original input can be decomposed into dz over dy. So the ratio of infinitesimal changes the final output to intermediate input, and then dy over dx. Okay? Because we can cancel out these two dy's from the right hand side. So we are left with just the dz over dx. That is one way to prove the chain. That is a basic idea of the chain. Right, so now let me show you several examples as an application of the chain. So how to take the derivative of this type of function. Okay? So the first example can be regarded as a composition between the outer function is x to the power 17. So f of x is x to the power 17. And the inner function g is the expression in the parentheses, 3x minus 2. All right, so this is nothing but f of g of x. Okay? This function f, outer function, has a g of x as the input. So the way to find the derivative is by the chain rule, we first take the derivative of the outer function. So 17 power comes up front, and we take 1 away from the power. So 17 becomes 16. Okay? And then we leave the inside function alone. So we just plug in g of x in the place of x. So x squared plus 3x minus 2. Okay? And then we multiply by derivative of the inner function. So g prime, x squared becomes 2x, 3x becomes 3, and negative 2 constant goes away. So 2x plus 3 is the derivative. That is the derivative of the first example. Right? It's a very convenient tool because we don't have to expand, this binomial expression. I don't even have any clue about how to expand this one. Okay? Nevertheless, we can find the derivative in a simple way. Right? Quite useful. And for the second example, we have dz over dx. We are asked to find dz over dx, where z is given by a function of y, and y is function of x. And so x is the original input, and y is a intermediate input, and z is a final output. Okay? So dz over dx is by the second expression of the chain rule, we can decompose into dz over dy times dy over dx. So dz over dx becomes the product of these two instantaneous changes, instantaneous rate of changes. So dz over dy, the derivative of z with respect to y, that is easy, just 3y squared. Okay? So let me open the separate note. dz over dy is a 3y squared. Okay? And then the second term, dy over dx. Oh, now y is given by division between two functions. So we have to adopt the quotient rule to find dy over dx. So first a denominator becomes a 6 minus x squared and is squared. Okay? And the top, derivative of the top, 2, and then multiplied by the bottom. Okay? And minus, remember this minus sign for the quotient rule. And we interchange the order. So 2x plus 3 and multiply by the derivative of the bottom. So negative x, yes. Okay. So dz over dx, meaning that we are looking for the rate of change of z, instantaneous rate of change of z with respect to x. So the answer should be function of x. So when we are asked to find dz over dx, that means we regard z as a function of x. Okay? So we have to translate this 3y squared into a function of x because y is given by this one. Okay? So 3y squared is 3 times x plus 3, 6 minus x squared, and raised to the power 2. Okay? So consequently, dz over dx, this guy, times this one. Okay? I think there is a way to simplify this expression, but that is just a additional work. It's not that useful and it's not that practical. So it's not that necessary to understand economic theory. So let me skip that. So that is the derivative of derivative of z with respect to x. All right. And I leave the third one for exercise. And so here we have several examples, several, applications of the chain rule. Among these, let me do just here. Let me show you two examples. This one, okay? So x to the power fourth times 2x minus 8 cubed, okay? So this is kind of, summary exercise. In order to find the derivative of this, we have to use all the rules we learned so far. Okay? So because we first take a look at this function, we can see that two functions of x are multiplied. So we start with the product rule to find the derivative. So here, so x to the y is given by x to the power fourth 2x minus a cubed. Okay? So regarding this is first function f of x, and this one is the second function g of x. So the product rule tells us the derivative of the product is derivative of the first, 4x to the power 3, and leave the second function alone, and plus, now we interchange the order, right? So we leave the first function alone. Now we have to take into account, we have to multiply by the derivative of the second. But the second function is given by one composite function. The outer function is x to the power, so x cubed, and the inner function is 2x minus 8. Okay? So now the chain rule kicks in here. So the derivative of the second is the first here, we have to consider derivative of the outer function. So 3x squared, but we leave the inside function alone. That is the derivative of the outer function, f prime of g of x. And then we multiply by the derivative of the inner function. That is 2. Right? 2x minus 8. 2x becomes 2 after taking the derivative. And negative 8 goes away as a constant. So we just multiply by 2. Okay, so I can simplify further because I can see some common factors here. So the common factors are x cubed and 2x minus 8 squared. Okay? So after factoring out these two, I will be left with 4x minus 8 from the first term. And from the second, I will be left with 1x here and times 6. So x cubed, x minus 8 squared, 8x plus 6x gives me 14x. And 4 times 8, negative 3. All right, so the derivative of this example is going to be this one. So for getting this derivative, I started with the product rule, and when we compute the derivative of the second function, this one, because second function is given by one composite function, I apply the chain rule. Okay? So at the first glance, finding derivative of this type of function looks very complicated. But after you keep doing exercises, you feel comfortable with that. It's just a piece of cake. Okay? And for this one, let me do, say, second example. All right, so y is given by function of u, and u is given by function of x. Okay, and we are looking for dy over dx. So the rate of change of y relative to so y is the final output of this composition, and x is the initial input. Okay? So we want to see how fast y increases or decreases as x changes. So now we use the second expression of the chain rule to compute dy over dx. In the second example, y is given by u to the power negative 7, and now u is in turn given by 1 minus x over 7. So dy over dx by the chain rule, this is dy over du times du over dx. Because these two du's will be cancelled. So with this y function, the derivative is negative 7. The power comes up front. And we take 1 away from the power, so the new power becomes negative 8. Right? and du over dx, the derivative of u with respect to x, 1 goes away, and x becomes 1. So we are left with negative 1 over 7. Oh, this is simple. So negative 7 will be cancelled by negative 1 over 7. So we are just left with u to the power negative 8, but this is not the final answer because we are looking for dy over dx, meaning that we consider y as a function of x. Okay? So the final answer should be a function of x. So to make this as a function of x, we can just substitute because u is given by 1 minus x over 7, 1 minus x over 7, raise it to the power negative. Okay? So that should be the final answer of this question. All right, and I leave the remaining examples for exercise, and I also post the answers to the remaining examples on the course website to help you do exercise. Okay, and okay, I spent 21 minutes, and let me explain the inverse function. So the one nice application of the chain rule is it helps us to find the derivative of the inverse function. So yeah, I'm not sure if you guys have heard about the inverse function, but the inverse function is, so suppose we have the original function f of x right here. So f associates a to 3, and f associates b to 1, and c to 2. Okay? That is a one-to-one function because whenever we have two different inputs, and the function's output will be different. Okay? So the one-to-one function is defined as whenever we have two different inputs, so A is different to B, then the function's output will be also different. F of A will be different from f of B. Then we say the function is one-to-one. Okay? And for this type of one-to-one function, we can change the order. So we can think of the inverse of this relation, just as the inverse matrix in linear algebra. Yeah? So one-to-one function can be reversed to send the output y back to input x, which is called the inverse of function f, and denoted by f superscript -1 of y. Yeah? So now the codomain of the original function f becomes the domain in the inverse function. So we have 1 to 3 on the left, and the original domain becomes the codomain. So the range of the function f superscript negative. So the original function was f of a is a 3, right? So the inverse function of 3 becomes a. So inverse f associates number 1 to letter b, and because b was associated to number 1 in the original function f, so f inverse of 1 leads us to letter b. Okay, and finally, so 3 is a, and 2, so f of c was equal to 2, so f inverse of 2 is equal to c. Okay? So it brings us to c. So that is the inverse function. And the one fact about the inverse function is the next. If we compose the function f with the inverse function, so f of f inverse, that is should be identity function x, just as a inverse matrix times A. So A inverse times A is an identity matrix in linear algebra, and composition of original function and inverse function should be equal to identity matrix. So I think this is quite straightforward, but let me show you one example using this too. So here, the original function starts from ABC, and codomain is 1, 2, 3. And the inverse function uses 1 to 3 as input, and ABC will be the outputs. So the original function was this, this, okay? And the inverse relates 1 to B, and 2 to C, and 3 to A. Now you can easily see that A by the function f gives us number 3, and by the inverse, it is back to A. Okay? And the letter B, we first, it translate to number 1, then by the inverse function, translate to transformed to letter B. So back to B and C as well. So now you can easily see that f of f inverse or f inverse of f should be identity function x. Okay? That is another definition of the inverse function. Okay. So inverse function is only defined for such a one-to-one function. If the function is not one-to-one, we can define the inverse function. So now going back to xy coordinate system. So if we consider function f of x defined on a real number, so x is now any real numbers. Okay? And the function is going to be one-to-one if and only if it is strictly increasing or decreasing. So, excuse me, y equals, say, x minus 1. That is monotonely increasing over the domain, so over the real number. So that is a one-to-one function. But y is x squared, is x squared. That is not one-to-one because, uh, you know, although we have two different inputs, negative 1 and 1, this function gives us the same value 1. Okay? So the problem with this function is initially decreasing in this quadrant, is increasing in the first quadrant. So it's not monotone decreasing. So neither monotone decreasing or nor monotone increasing. So this is why this function is not one-to-one. So this type of function does not have the inverse. Okay? But this function has the inverse. So the way to define increasing function is whenever we have a higher input, so x1 is higher than x2, the output is also higher. And we say f is increasing. If the inequality is reversed, we say function is decreasing. Yeah? But in either case, the inverse function exists. So as either case is the function will be a one-to-one function. So inverse function exists. So we are studying how to take the derivative of the inverse function, but in order to find the derivative of the inverse, I have to digress a little bit, right? So let me first illustrate the derivative test for monotone functions. Now that is quite important. So that is about, it concerns about, um, so what kind of information we could obtain, sorry, we could obtain from the derivative, from the sign of the derivative. Okay? So it turns out that the sign of the derivative conveys very important information about the shape of the original function. So, so if the sign of the derivative is positive, that means the original function is strictly increasing. If the sign, on the other hand, if the sign of the derivative is negative, it means f is strictly decreasing, right? This is quite intuitive. It's not surprising at all because think about this region. So think about this function. And so it is initially decreasing, and increasing on over this interval. So in this interval, and then now decreasing again, and back up increasing. All right. Because the derivative delivers information about the slope of the tangent. So whenever a function is decreasing, we can see that the slope of the tangent will be negative. Okay? So in other words, the derivative must take a negative sign in this interval. Okay? But in this between these 2 points, local minimum and local maximum, the function is increasing. So in this over this interval, on this interval, the slope of the tangent will be positive. In other words, the sign of the derivative will be positive. Okay? So because the derivative is the slope of the tangent, so from the sign of the derivative, we can infer whether function is increasing or decreasing. Yeah? Let me show you one example. Here, f of x is given by one cubic function, x cubed minus 12x minus 5. And we are asked to identify the interval on which function is increasing or decreasing. Okay? And then, once again, whether function is monotone increasing or decreasing, it bears on the sign of the derivative. So we first compute the sign of the derivative, f prime. So we first compute the derivative. So f prime is x cubed becomes a 3x cubed, and negative 12x becomes negative 2. And negative 5, that is constant, so it goes away. Right? So that is the derivative of the original function. So I can factor out 3 and x squared minus 4. Okay? And using the formula, a squared minus b squared is a plus b times a minus b. So I can rewrite this 3 times x plus 2 times x minus 2. So now we examine the sign of the derivative to tell on which interval function is increasing or decreasing. And then we can see that there are two critical points, 2 and negativity. So let me draw the horizontal line. It is a horizontal axis. So it stands for the value of x. And we have here two critical points. So at which the function, the derivative of this, the sign of the derivative will change at these 2 points, negative 2 and 2. Okay? So whenever x is lower than negative, say negative 3, if we examine the sign of the derivative at negative 3 by substitution, then the derivative takes the value 3 times at this point, 3 times negative 1 times negative 5. It is positive. So we can infer on this interval, whenever x is lower than negative 2, the derivative is positive. F prime is positive, meaning that function f is increasing. And between negative 2 and 2, now say 0, the derivative takes the value of 3 times 2 times negative 2. That is a negative number. So tells us derivative is negative on the interval between negative 2 and 2, meaning that original function is decreasing. Yeah. And finally, when x is higher than 2, x is larger than 2, say 3, then we can substitute 3 for x to find out the sign of the derivative on this interval. That is kind of a test point. Okay? So 3 times 5 times 1, that is positive. So f prime will be positive on this interval, meaning that it's increasing. So by investigating the sign of the derivative, we can infer the shape of the function. So the function initially increasing until point -2. So after this point, it starts decreasing. But whenever x is larger than 2, now it is back up increasing. So cubic function looks like this. So whenever derivative is positive, it tells us function is increasing. If derivative is negative, it tells us the original function is decreasing. Okay? So the sign of the derivative tells us whether original function is increasing or decreasing some given. Right? And the basic idea is because the derivative is the slope of the tangent line. If the slope of the tangent line is a negative, it means function is decreasing at the instantaneously decreasing. Or if the sign of the tangent line, the slope of the tangent line turns out to be positive. So in other words, the derivative takes a positive value, meaning that the original function is instantaneously increasing at the. All right, so that is the derivative test for monotone functions. And the way to prove this, that is from the mean value theorem. So the mean value theorem is the counterpart of the intermediate value theorem we studied in the previous week. So intermediate value theorem is a immediate consequence of continuous function, but whereas the mean value theorem is a immediate consequence of differentiable function. So the mean value theorem tells us whenever y is given by f of x, this function is differentiable on interval between a and b. Okay? So we have a one smooth function that is differentiable on the interval between a and b. Right? Then we can compute the rate of change over this interval. That is f of b minus f of a. The function changes from a to f of b over this interval. Okay? But the x changes by b minus a. So x moves from a to b. So the change in x on this interval is b minus a, and change in y is f of b minus f of a. So that is the rate of change over the interval between a and b. Okay? And the mean value theorem tells us there is a one point C between A and B. The slope of the tangent at that point is the same as the rate of change. So in other words, in terms of the derivative, f prime of C, so at this point, C, the slope of the tangent is the same as the rate of change, meaning that this tangent and the sequent connecting the 2 points, the left-hand point and the right-hand point, are parallel to each other. Okay? So using this mean value theorem, we can easily prove the 7 point. So the derivative test for monotone. So whenever x2 is higher than x1, and then the mean value theorem applied to f tells us, so whenever x1 is higher than x2, so if we consider rate of change between x1 and x2, that is going to be this one, right? And by the mean value theorem, there is a one point C between x1 and x2, so at this point, the derivative takes the same value as this rate of change. Okay? And suppose that f prime is a positive between x1 and x2. Okay? Any point. So f prime is a positive at each point of uh, each point of the interval between a and b, so x1 and x2. Okay? So this is positive. And okay, so this one is positive. So x2 minus x1, because we assumed x2 is higher than x1, that is positive, right? So if we examine the sign of this, yeah, so f of x2 minus f of x1, that is f prime c times x2 minus x1. I just multiply both sides by x2 minus x1. Okay? And this is positive by assumption, as we assume the function f, the derivative of f takes a positive value on the interval between x1 and x2. And x2 minus x1 is a positive because we assume x2 is higher than x1. So the right side becomes the product of two positive numbers. So we can make sure this one is positive. So that shows us f of x2 is higher than f of x1 whenever derivative is positive. Okay? So that proves the first statement, and you can prove the second statement by the same argument, same token. Okay? So since f prime is a positive by assumption, we must have of x2 higher than f of x1, meaning that whenever derivative is positive, function is increasing on. So why did I do this? Because you know, the first derivative test, the sign of the derivative tells us whether function is increasing or decreasing. So it tells us whether the original function has the inverse function or not. Yeah? So I kind of take a wide detour to get back to the our original topic, how to take the derivative of the inverse function. All right. So here we have a one original function y equals 5x plus 25. And now from the derivative test, y prime, that is 5, is always positive, meaning that this function is monotone increasing, so 1 to 1, so the inverse function exists. Yeah? And the way to find the inverse is we first solve the original function for x. And so y is given by 5x plus 25, and we solve for x. So moving 25 to the left, y minus 25 equals 5x, and then solve for x, y minus 25 over x. Oh, sorry, for over 5. Okay? And then we interchange x and y. So y equals x minus 25 over 5. That is a f inverse of x. Okay? If I call the original function f of x, and this is going to be f inverse. We can verify this fact. So once again, remember the inverse function is the composition of f and f inverse should be identity function x. Okay? So the inverse function turns out to be x minus 25 over 5. And we have a original function 5x plus 25. So the composition with a f as the outer function. Now f of f inverse is 5 instead of x. We substitute this quantity. So it's minus 25 over 5 and plus 25. So 5 will be cancelled. So we have negative 25 also cancelled. And we just left with x, identity function. That verifies this is indeed the inverse function of the function 5x plus 24. Okay? So the way to find the inverse is we first solve for x, and then interchange x and y. Okay? And similarly, we can do the same exercise for this one. So now this stands for demand function. So demand function as a function of price. So this demand function tells us at each price of P, how many person and or how many units will be purchased by consumers. All right. So we can check the this function is monotone decreasing whenever P is positive using the derivative test. Okay. So we find the derivative of d prime, and by the quotient rule, on the bottom, we have 3p plus 5 squared. And on the top, the derivative of the top is 1. P becomes 1, 7 becomes 0. Then we multiply by the bottom, 3p plus 5, and minus p plus 7 times the derivative of the bottom, 3. Okay. So 3p plus 5 squared as the denominator. Now we can simplify the numerator. 3p plus 5 and distributing 3 minus 3p minus 21. So we have negative 16 on the top, 3p plus 5 squared on the bottom. And we don't have to check the sign of the bottom because something squared is always positive. Okay? So the sign of the derivative only determined by the sign of the top, but we have a negative number on the top, meaning that d prime is a negative value, always, no matter what p. Okay? So meaning that the demand function is a decreasing over p. So it has this shape. So the way to find the inverse now, all right, so let me call the output Q. So here Q stands for the quantity demanded at given price P. Okay? And then we first solve for P. So P plus 7 equals, I can move this denominator to the right side by multiplying both sides by 3P plus 5. So Q times 3P plus 5. Trying to solve this equation for P. Okay? So P plus 7, now distributing Q, 3QP plus 5Q. Okay? And then collect P terms on the left-hand side. So P minus 3QP equals 5Q minus 7. Okay? So collect P terms on the left-hand side and move the other terms to the right-hand side. Okay? Separate the P terms and the non-P terms. And I can factor out P from the left. 1 minus 3Q equals 5Q minus 7. And so consequently, P is a 5Q minus 7 over 1 minus 3Q. Okay? And then interchange input and output. So Q becomes 5P minus 7 over 1 minus 3P. This is the inverse function of, this is the inverse demand function. Okay? So once again, the way to find the inverse function is we first solve for input in terms of output, and then we interchange input and output. So finally, finally, oh, this video is way longer than I had expected, but let me finish this one. So suppose that y is given by some differentiable and with a non-zero derivative on interval between a and b. Non-zero derivative means the derivative of f of x is either positive or negative So the function is a monotone increasing or decreasing. Okay? So that, which in turn means that f of x is invertible. Inverse function exists. Okay? So the theorem tells us f is invertible. So f inverse exists on interval between a and b. And the derivative of the inverse, so f inverse prime, is a 1 over f prime, right? And the way to see this is, remember, the f inverse and f of x, composition between these two is always equal to identity function. Okay? Now let me take the derivative of this equation with respect to x. Okay? And we have the composition on the left-hand side. So now let me use the chain rule to find the derivative. And the derivative of the outer function, yeah, and then leave the inside function alone. Then we multiply by the derivative of the inner function. That is the derivative of the left-hand side. Application of the chain, right? And the right side, x derivative is just 1. Yeah? And then f of x, that is a just y, the output y. So consequently, f inverse derivative, the argument is y, yeah? The original output of the function f of x. Yeah? That is 1 over f prime. Yeah? So it tells us the derivative of the inverse is the reciprocal of the original derivative. Okay? The derivative, inverse derivative is reciprocal of the derivative of the original function. All right, so let me stop the video with this example. Right, so given the function y equals x squared minus 2x, find the derivative of the inverse at x is equal to 1. So the way to find the derivative of the inverse, we can start with a we can begin by uh, finding the inverse function of this uh, by taking these two steps. So first solving for x in terms of y and interchange x and y to find the explicit form of the inverse, okay? And then take the derivative. Okay? But the inverse function theorem tells us a leeway. There is a much leeway to find the derivative of the inverse. Okay? So the derivative of inverse at 1, because at 1 this function takes the value of 1 minus 2, that is negative 1. Okay? Now we are looking for uh, the inverse derivative at negative 1. Okay? Which is a 1 over f prime of x. So f prime of 1. Input is 1. Okay? X is value. And the corresponding output is negative 1. Okay? So uh, the derivative is f prime is 2x minus 2. So at this point, at this point, this is a 0. X minus 2. And 0. That is a infinite. Hmm. Let me think. Squared minus 2x. Oh, yes. You know what? disregard this example. I made this example by myself, but turns out that there is a very serious problem with this example. So please disregard this example and let me stop the second video here. And so let me illustrate the one application of the inverse function that is about the price elasticity at the live lecture. I'm sorry about that, this example, but let me stop the video here.